This is the 21st video in our series on Lie algebras, and we're going to talk a little bit more about root systems today and basis for a root system, or sometimes called a base for a root system. And this is all working towards a nice classification theorem, which we'll probably end this course with. Okay, so let's recall a definition first. So a subset R of a real inner product space E is a root system if the following four things are satisfied. So the zero vector is not an element of R, the number of elements in R is finite, and R spans E. And then also, if alpha is in R and a multiple of alpha is in R, then that multiple is just plus or minus 1. So for instance, if alpha is in R, we know that 2 alpha or 3 alpha, etc. are not in R. Next, if alpha in R, then this map S alpha, which takes x to x minus 2 inner product of alpha with x over inner product of alpha with alpha in the alpha direction, that map, which is a reflection through a hyperplane that permutes the elements of R. Okay, and then one last thing, if alpha and beta are in R, then this like bilinear form, beta alpha, defined by 2 alpha beta over alpha alpha, is an integer. And then maybe a new part of this definition is what it means for this R, this root system, to be irreducible and reducible. So we say it's reducible if we can write R as the disjoint union of R1 and R2, where those are also root systems, and we take the alpha beta must be equal to 0, that inner product, if alpha is in R1 and beta is in R2. And then if a root system is not reducible, then we say it's irreducible. So our first important result here is essentially saying, well, that we only have to look at irreducible root systems. And that's because we can decompose any root system into a disjoint union of irreducible root systems. And that's what this lemma says. And furthermore, if our root system is a root system for our inner product space E, then each of these irreducible root systems are root systems for EI. And furthermore, if you take the direct sum of these EIs, you get our original inner product space. So that's nice. Okay, so how does this proof go? Well, let's define what will be an equivalence relation. I'll call this equivalence relation tilde, and this is going to be defined on our root system. And it's going to be defined by the following condition. So we'll say that alpha is equivalent to beta if and only if we have this string of roots satisfying the following rule. So if we've got this gamma 1 up to gamma m, so that alpha is equal to gamma 1, beta is equal to gamma m. So in other words, we've got like a first one and a last one. And then we have all of these inner products, gamma 1, gamma 2, gamma 2, gamma 3, all the way up gamma m minus 1, gamma m are all non-zero. So that's our equivalence relation. And then, well, let's see. If we've ever got an equivalence relation, we know that we can decompose the set on which that equivalence relation acts into equivalence classes. And those equivalence classes are disjoint. So in other words, we can do R is equal to this disjoint union, R1 disjoint union R2, all the way up disjoint union Rn, where those are, like I said, equivalence classes. So in other words, maybe Rk is the equivalence class of alpha k. And well, if you remember anything about equivalence relations, you only need one equivalence class representative. Okay, so now, well, that's going to bring us to a claim which will do a lot of the heavy lifting right here. And that claim is that RK is a root system for what I'll call EK, which we'll just define that EK to be the span of RK, because we have to define the inner product space somehow. And well, that means that we've fulfilled, well, actually both of these rules here. Because since the original R was finite and it didn't contain 0, then that means that upon this new, assumption right here, we have this first bit of being an inner product space already. Okay, so let's see how the little proof of this claim goes. So like I said, we need to prove these 1, 2, 3, 4 things. So let's just lie them out. So 1 is done by what I just said. And now what about 2? So if alpha is an R and C alpha is an R, then C is equal to plus minus 1. Notice that that follows maybe really just as simply based on the fact that that held in our original R, and this RK is really just like this decomposition of our original R. So there's no way you could get any other kind of multiple of alpha inside of these RKs. Okay, now what about 3, which is this thing about hyperplanes or reflections in hyperplanes being permutations of root vectors. Okay, so let's see how that might go. So let's suppose that alpha and beta are in RK. And then let's note, if we do S alpha applied to beta, we get the following object. So it's going to be beta minus 2 inner product of beta with alpha over alpha alpha in the alpha direction. And this is inside of R. And we know it's inside of R because this was a permutation inside of the big root system. And then also, we know that there exist what I'll call these gamma 1 up to gamma m, satisfying this, well, essentially this rule up here. So alpha is equal to gamma 1, beta is equal to gamma m, and then we have alpha with gamma 2, and then gamma 2 with gamma 3, all the way up to gamma m minus 1 with beta. These things are non-zero. And that's just by the definition of alpha and beta being equivalent. And we know they're equivalent because they're in the same equivalence class. But now let's do the calculation. Let's see, S alpha applied to beta, and then S alpha applied to gamma. But then plugging our formula up here for this S alpha function, and then using the linearity of this inner product, we'll see that that turns into beta gamma. That's from the beta part right here. And then the corresponding gamma part for this S alpha gamma. And then, well, we're going to have a bunch of other terms here as well. And those are just going to be from the cross terms from this expansion. Maybe it'd be a nice little homework exercise to work those out. But the nice thing here is that these cross terms all cancel. So these cross terms cancel here. So, well, what does that tell you? Well, that tells you that the inner product after applying this reflection by alpha is the same thing as it was before. But what that means is that we've got this nice string of alpha and then S alpha applied to itself, keeping in mind that S alpha applied to itself is minus alpha. That's something that we did before. And then that's S alpha applied to alpha with S alpha applied to gamma 2. And then all the way up here at the very end, we have S alpha applied to gamma m minus 1 with S alpha applied to beta. These are all non-zero. And they're all non-zero because, well, the original ones were non-zero as well. Oh, this should have been non-zero. I think I said it out loud, but I didn't write it correct. Well, up here it's non-zero as we see. But notice that that being non-zero means that we've got this equivalence between S alpha beta and, well, alpha and beta. But that equivalence via this equivalence relation is exactly what it takes for S alpha beta to be inside of our RK. In other words, this S alpha built out of something from RK permutes elements of RK. Okay, so that takes care of this third bit. Now let's move on to the fourth. So now moving on to this fourth thing right here. So I'm not going to say much about that because that holds like immediately clearly as well. Because if alpha and beta are in RK, for instance, then they're in R. But just looking at them in R, you get this object is in the integers just as you need for RK to have that rule of being a root system. Okay, so next up what we need to show is that these inner product spaces, EI, built out of these RI, well, that they direct sum to our original inner product space. So in other words, the last thing we need to show is that E is equal to E1 direct sum E2 all the way up direct sum En. So let's notice that we already know part of this. And the part that we know already is that E is equal to E1 plus E2 plus all the way up to En. So a potentially non-direct sum. And that's, well, because of this rule right here in the definition of root systems. And so now we just have to show that these EIs or EKs, whatever you want to call them, maybe that they overlap only at the zero vector. So let's maybe take a vector V from EI intersect EJ. And then let's look at the inner product of V with itself. And now, well, let's observe that looking at V inside of EI on this side, and then looking at V inside of EJ on this side, will tell us that we get 0 here. And that's because V is made up of linear combinations of, well, things from Ri and Rj, and we know that those have this inner product of 0, well, actually built out of our equivalence relation on the last board. Okay, so that means that, well, the only vector in an inner product space whose inner product with itself is 0 is the 0 vector. So that means we get V is equal to the 0 vector, but that means that EI intersected with EJ is simply the 0 vector space. But that's the last thing that we needed to show to get this sum to a direct sum. Okay, so now let's move on and talk about a base of a root system. Okay, moving on to a base of a root system. So a subset B of a root system R is called a base of this root system if B is a basis of the corresponding vector space E, which is the span of R. And then next we've got this kind of really interesting condition which says that every root beta can be written as an integer linear combination of elements of the base. So that kind of makes sense based off of, you know, the choice of words here. But not only that, but all of these weights of the integer linear combination have the same sign. And if that sign of the, well, non-zero terms is positive, then we say that beta is a positive root. If it's negative, we say that it's a negative root. And then furthermore, elements of B are often called simple roots. Now, next up, what we want to show is that the angle between any two simple roots is obtuse. And, well, geometrically, that means that that angle should be on the interval from pi halves to pi. So notice we will not include pi because that would be like the negative version of the root, but we can include pi halves. Okay, so let's see how this goes. So let's take two simple roots, which I'll call alpha and beta, and then we want to look at this thing S alpha beta two different ways. So notice that S alpha beta is equal to beta minus 2 times the inner product of alpha with beta over the inner product of alpha with itself in the alpha direction. And so, well, that's just by the definition of this S alpha. But then let's also note that S alpha beta is in R, which means that S alpha beta can be rewritten as, well, let's see, it'll be rewritten in the form, the sum over, well, I'll just put some index I here, and then Ci times alpha I, where, well, I guess like understood here is these alpha I are in B. Okay, so that's just by this condition right here. And furthermore, all of those Ci's have the same sign. But since we're in vector space kind of in a broader sense, and we've got this basis condition right here, that means that this expansion right here for S alpha beta and this expansion right here for S alpha beta are really the same, because those are writing, well, S alpha beta as a linear combination of elements from B. Well, here you just need beta and alpha, so here you also just need beta and alpha. So that means here, this is just equal to C1 alpha plus C2 beta. But then C1 alpha and C2 beta have the same sign. But that means that, well, this coefficient here, which is 1, which is positive, has the same thing as this coefficient here, which is minus 2 alpha beta over alpha alpha. But that means that this 2 alpha beta over alpha alpha must be negative to cancel out this minus sign here. But the only thing building the sign here is this beta alpha. So in other words, we need beta alpha to be less than or equal to 0. And like I said, that's because we need these two things to both be positive. Well, the coefficient here to be 1, and then this term right here to be positive as well, because we know that these have to have the same sign, and this is always fixed or already fixed at a positive 1. But then let's recall that this beta alpha can be rewritten as alpha alpha times beta beta times the cosine of theta, where theta is the angle between alpha and beta. But putting this together, we see that that means that the cosine of theta is less than or equal to 0. But when talking about an angle between vectors, that tells us that the only possible values of this angle come exactly from the interval that we were looking for. In other words, obtuse angles. Okay, so now let's look at a quick example. Okay, so for our example, let's recall that a root system of SLN is given by this plus minus epsilon I minus epsilon j, where I is always less than j, and they're both between 1 and n plus 1. So we looked at this before. And now let's notice that the following thing, in fact, is a basis for this root system, or a base of this root system. So I'll call this alpha 1 up to alpha n, and I'll say that alpha I is equal to epsilon I minus epsilon I plus 1. And so, well, let's make sure that this is the case, and we'll do that by taking this kind of arbitrary element of the root system, so this epsilon I minus epsilon j, and observe that we can write that as alpha 1 plus, or sorry, alpha I plus alpha I plus 1, all the way up to alpha j minus 1, with an adornment of a plus or minus out front to take care of this plus or minus out front. And I think that's pretty clear that that's exactly how these root strings, alpha I added all the way up to alpha j minus 1, will maybe combine together. Now I'd like to point out that if we take a plus here, you get a positive root, and if you take a minus out here, you get a negative root. So let's just say that this is an element of R plus, whereas this would be an element of R minus. So we've got a nice picture of what the positive roots and the negative roots and the simple roots look like in the case of SLN. Okay, so now let's prove our main result for the day, which is that every root system has a base. Okay, so like I said, now we're going to prove that every root system has a base. So let's let R be a root system. And here we'll just take E to be equal to the span of R, and we'll make sure that the dimension of E is bigger than or equal to 2. If the dimension of E is 1, then, well, you have something very simple and you kind of clearly have a root system. Okay, so next up, let's take an element which I'll call Z from E such that the inner product of Z with alpha is always non-zero. And this is going to be true for all alpha in R. So in other words, this vector is not perpendicular to any of the roots. So this may be something that you need to convince yourselves of, but it'd be a good exercise to convince yourself that this is true. Or it's possible to be able to bring about this vector Z. And now we'd like to define this thing that's called R plus, and that's going to be all alpha in R, where if you take the inner product, you don't get something that's non-zero, you get something that's positive. So this is going to eventually play the role of the positive roots. And now what we'd like to do is build a basis out of this. So let's set B equal to alpha in R plus such that alpha is not the sum of any two elements from B. So in other words, you can't like decompose alpha into, for instance, beta plus gamma, where beta are both in R plus, I should say. So this should be from R plus. Okay, so eventually we'll show that B is a base. Okay, so let's get to that. So now let's take what I'll call a beta inside of R, and what we want to show is that beta is equal to the sum over alpha in B of C alpha times alpha, where C alpha are all the same sign. So that's this condition over here of being a base. Okay, and so let's notice that either we have beta is in R plus or beta is in R minus, which I guess I haven't really defined R minus yet, but you can imagine how R minus might be defined. It would be defined where you get a negative here. Okay, so without loss of generality, we would have beta in R plus. Because notice if beta is in R minus, we can just replace beta with minus beta. So like I said, we may as well assume that beta is in R plus. But that means that we want this same sign to be in fact bigger than or equal to 0. So the ones that are non-zero have to be positive. Okay, so now by way of contradiction, let's suppose at least one of the C alphas are negative. And well, where do these C alphas come from? Well, they come from this like spanning up here. So we know that we have spanning. And so what we'll just assume is that, well, what if we get this maybe sum here, but we can't get them all with one sign. We can't get them all with a non-negative sign. We have to use a negative number in there. But if we have to use a negative number here for one of these betas, then that means that we have to use a negative number for some collection. Maybe that collection is only this single beta, but for a collection of betas. So among all such beta in R plus, and when I say all such, I mean all such that require this negative weighted component, this negative C alpha, let's choose the one that minimizes some condition. And that condition is the following. So it's gonna be this number, the inner product of Z with beta. So we're minimizing that thing which is a positive number. Okay, so now next up, what I'd like to do is note that beta is not an element of B. Well, I guess if it were an element of B, we'd totally be done already. So what we'll do is assume that it's not an element of B. But then by this condition defining B over here, that means that beta can be written as beta 1 plus beta 2 with, these beta i's in R plus. That's that definition of B over there. But now let's maybe pick the choice of naming of these beta 1, so it requires a negative, maybe I'll just call it weight here, to one of our elements of B. So it requires one of these things to be negative. But then let's observe that the inner product of Z with beta 1 is most definitely less than the inner product of Z with beta. And that's because the inner product of B with beta, or Z with beta 2, was also positive, so that's strictly less. But then this is also bigger than 0 because beta 1 was in R plus. But observe that this is a contradiction of the minimality of that inner product of Z with beta. So what have we contradicted? Well, we just contradicted the need for a negative weight right here, which means that we don't need any negative weights, meaning this condition of the C alpha being all the same sign is holding right here. Okay, great. So now next up, what we want to show is linear independence of B as a basis for E. So it kind of already spans, well, based off of this thing that we did right here, given the fact that E is the span of R. Now we need to, do the next part of being a basis, which is linear independence. Okay, now moving on to showing that B is linearly independent, let's suppose we have the sum over alpha and B of C alpha times alpha is equal to 0. So we've got a would-be linear dependence relation. And now, well, let's set X equal to the following. So this is going to be the sum over alpha and B with the condition that C alpha is positive of C alpha alpha. So this is the positive part of this sum. But notice that since the sum is 0, then that's also the negative part of, well, the negative part of this sum. So, well, that's good. And now, well, we're summing over these alpha and B where C alpha is negative, but let's maybe change the index here so it's maybe not as confusing. So we'll say beta and B where C beta is negative, and then we'll have C beta beta here. So that's just re-indexed a little bit. Okay, so now let's calculate the inner product of X with itself. But now using linearity of the inner product, that's going to give us the following. So we'll have minus, and then the sum over alpha and beta, where C alpha is positive, C beta is negative, of C alpha times C beta times the inner product of alpha with beta. But now let's observe that this C beta is negative, this C alpha is positive, this minus sign, well, that makes C beta, C alpha, and this minus sign positive. This alpha beta is less than or equal to 0 by our previous thing about the angle being obtuse, making this whole sum less than or equal to 0. Again, we've got 3 minus signs there. Minus here, a minus inside of the C beta, and then a minus from the alpha with beta. But the inner product of XX, well, we know that that's bigger than or equal to 0 by the tenets of an inner product space, which means we know the inner product of X with X must be equal to 0. In other words, we know that X must be equal to 0. But now that means that 0 is the same thing as the inner product of X with Z, where Z was chosen as before, as this up here. But then again, by the way that we've got linearity of an inner product space and this guy right here, we know that that's going to be the sum over alpha and B, where C alpha is positive, of C alpha and then alpha inner producted with z. But then we know the product of alpha with z has got to be positive, given the fact that alpha is in B and B is a subset of R plus. But we're adding a bunch of positive numbers together to get 0 with these weights C alpha, but that means that all of those weights C alpha, which are all bigger than or equal to 0, are in fact all equal to 0. So that means that all of these C alphas are equal to 0. But then by a really similar argument, all of these C betas are also equal to 0. But that means that everything over here, every coefficient over here is equal to 0. But that's exactly what we need for the finishing of this linear independence argument. Okay, so now let's leave everyone with some exercises. Okay, so here are a couple of exercises. So the first says that if you have a base for a root system, if you apply one of these reflections through hyperplanes, S alpha, to every element of the base, you get another base for the root system. So that's pretty cool. Next up, let's say you've got a positive root and any root that is different than that positive root. Then if you take the reflection S beta applied to alpha, you also get a positive root. And then before we leave everything, I just want to note some other standard notation. So capital Phi is often used for a root system. And then capital Phi plus are the positive roots. Capital Phi minus is often the negative roots. And finally, delta is often the base, or often called the simple roots. And that's a good place to stop.